Okay, hello everybody. My name's Andy Gooding. I'm the Vice President of Engineering at Aerospike. We make a database. Some of you may even use it. I've been there for 8 years, so almost from its very beginning. Before that, I spent many years doing a lot of other kinds of software, mostly embedded systems like phones and set-top boxes. And if you go far enough back, you find that I'm not really a computer scientist. Originally, I was a theoretical physicist, so I came to this from a different angle from most people. But don't let that worry you. 2 years ago, we added a big feature at Aerospike. We added strong consistency as an option. When we did it, we tried a very novel approach for what we thought were very good reasons, and we still think are very good reasons, and it worked out really well. We think our system is great, it works, it actually guarantees strong consistency. But this talk is not about Aerospike strong consistency, it's just about strong consistency in general. So really it's about what is it, what does the guarantee mean, do you care, what are the alternatives, what does it mean for you as a developer or a DevOps, what does it mean in operation maybe, what are the trade-offs with the alternatives. So yeah, let's get to it. So I said I wasn't a computer scientist, and that's true. But if you are, or you were, you went to school in it, you've probably heard of this thing called the Cap Theorem. I'm not going to prove it here, although maybe by the end of the talk you'll have some sense as to why it's true. The letters in Cap are for, the C is for consistency, the A is for availability, and the P is for partitioning. So we're talking about databases that are clusters, and the P is, when we say cluster partitioning, it means that the cluster kind of breaks up or isn't all there. The C, which is consistency, I've modified with strong consistency for reasons that may become apparent later. But anyway, what does this mean? The theorem basically says that there are these three things, and when you have a distributed system database, you get to choose any two, as long as one of them is P. And so that doesn't seem fair. C and A sound pretty cool. Consistency sounds cool, availability sounds cool. Cluster partitioning does not sound cool, so why do I have to choose that one? And the reason is because in the real world, you don't really have a choice. Partitions just happen. Nodes go down, and it doesn't necessarily mean that your software isn't perfect. It can be hardware, it can be someone kicked the plug out, but nodes will go down. And also, any of you that have any experience with networks know that connections are not perfect. Eventually, something's going to happen, connections will break. And usually when people are discussing CAP and cluster partitions, this is kind of what they're talking about. They're talking about split brain scenarios, where some of the cluster can't see the rest of the cluster, or the clients can't see the cluster server nodes. But at some level, if you have a node that nothing can see it, it may as well be down, and so nodes being down also kind of count as partitioning. So this is just going to happen, and most of you in here probably already know this, so I don't have to try and convince you that you just got to choose P. It's not really a choice. So really it comes down to you're going to choose consistency or availability. So again, consistency we'll call strong consistency, availability, maximum availability. Strong consistency is actually very well defined. It has, I think, a pretty clear definition, which I'll show you in a minute. And maximum availability. One thing I want to point out there is that it doesn't mean 100% availability. Availability, no matter what you do, the sad news is that it can always go to 0 if someone blows your cluster up or all your clusters up, or the power goes out. You're going to end up with 0 availability, no matter how good your hardware and software is. So A is really maximum availability, and I'll tell you what I think that means also in a minute. Okay, one other thing or a couple other things I want to point out is that, yeah, you have to make this choice, but it might not be as dire as it sounds. It doesn't mean that if I choose C in every single possible scenario where the cluster isn't whole that I'm going to lose availability. And conversely, choosing A doesn't necessarily mean that every scenario breaks consistency. Most good distributed systems should be able to tolerate a certain amount of P without actually sacrificing either one, whether it calls itself a CP or an AP system. In particular, most of them should at least allow you to upgrade your cluster. So take one node down at a time, or however many nodes down at a time. Do a rolling upgrade without sacrificing either consistency or your 100% availability, or your maximum availability. So it's really, the choice is about what happens when things get worse. Okay, so promised you a nice clean definition for strong consistency, so here it is. In simplest terms, what it means is that from the point of view of the clients, the outside world, a given record, it has only a single linear progression of the record version and its content. And that may sound kind of obvious and trivial, like, isn't that what all databases do? And it turns out no. In distributed systems, it's not actually a given or trivial that this happens, but this is one half of the definition of strong consistency. So these, I drew a string of versions there with operations. Each operation is a write. Essentially, it's looking at the current version of the record, and it takes you to a new version of the record. It could literally be an atomic operation, or it could be 2 transactions where you do a read, modify, write with a generation check. But the idea is that you're going from one version to the next, and almost all the time, it depends on the previous version of the record, what the next version of the record is going to be. So the other part of the definition is that any operation that you do that is acknowledged as successful to any client has to be reflected in the progression and never be lost. So that's a long way of saying don't lose writes. If I did this thing and it succeeded, it better not, evidence of it better not magically disappear later on or not be visible from another view. So to me, this is strong consistency. There are some nuances concerning read-only operations and the version progressions you see there. I'll come back and talk about that later, but I don't want to kind of muddy up what I think the actual definition of strong consistency is. So, okay, what's maximum availability? In simplest terms, that means that my operations are going to succeed as long as any part of the cluster is visible. So, for example, I may have a bunch of connection failures. Even if I can only see one node from a given client, my operation is going to succeed on that node. So it really is saying that, I'm just going to, whatever I can see, I'm always going to go ahead and just do the operation, even if I can't see the whole cluster, even if I can only see one teeny piece of it. Okay, what that pretty much means is in an AP system where you've chosen maximum availability, you are going to allow the record progression that we just talked about, the single linear progression in strong consistency. You're going to bag that. You're going to allow the record progression to split. And the way that happens is really that pretty much what's going on is you're using replication. So a copy of your record, there's just not one copy of your record in the cluster. It's usually two or more, and they're on different nodes. And when you get these split brain scenarios, what can happen is different clients see different replicas. And they start the same, but if the different clients start doing operations on different replicas, because they're the ones you can see, then you'll get different lineages. So the record progression will split. It can even be one client that ends up doing the split. If it just alternately sees one node and then another, and the two replicas resided there, you can do an operation in one. Then you can go back to the older version and do another operation that starts on the older version again. So that's the thing that you're going to allow. So by definition, that breaks consistency. So you can sort of start to see what the trade-off is here. So here's a drawing of a simple split. Those same four operations that happened, that I drew for you in strong consistency, 01 through 04. If it turns out that 01 and 02 end up starting on different copies of version 0 of your record, you end up with these versions here that just aren't the same thing as the versions that you saw in the strong consistency sequence. So VY is just missing 01, VB is missing 02 and 03. So you've already violated your consistency contract. Eventually, perhaps your cluster will mend itself, and so you'll take all the versions that split and you'll merge them together again. And sometimes, if you're really clever, you might actually even be able to recover V4. In other words, the exact record that you would have seen if none of this ever happened, none of the splitting ever happened, and you had guaranteed strong consistency. People call this eventual consistency, and it's sort of why we've kind of added the strong to consistency. As far as the Cap Theorem is concerned, the letter is C, and consistency means strong consistency. But since people call this eventual consistency, we kind of put the strong on the thing the Cap is talking about to distinguish it from this. So yeah, this is eventual consistency, the ability to take all your split lineages and merge them back together to make it as if all the splitting was just a bad dream and it never happened. So this graphic is the rainbow-powered flying unicorn. It's probably what got this talk into this DevOps meetup. I don't mean to imply that I don't believe in eventual consistency. It is a thing. But there's a lot of mythology surrounding it, and so it's probably worth, I'm going to spend a few slides on that, kind of explaining or talking about the mythology around it. So I've had conversations with people like potential customers for our database who say, I really love strong consistency, but if you can't give it to us, then that's okay. We can manage with eventual consistency. So just give us that. And I'll ask them, wait, you prefer eventual consistency? They, no. We would love strong consistency, but if you can't do it, we'll settle for eventual consistency. So, in their mind, it's this thing that's somewhere along the way to strong consistency, and it's as if they think, well, if you're trying to develop a strong consistency system, if you just kind of stop short, you have eventual consistency. And that's just not the case at all. They are very different unicorns. They They both have 4 legs and a horn on their forehead, and they're powered by rainbows, but the resemblance stops there. They're really very different things. And so, you know, I'm going to take you through a little bit of eventual consistency, and you'll kind of see why. So one of the big differences is eventual consistency is very use case dependent. It depends on what you're doing in these operations, how tractable it is to achieve eventual consistency. So I'll show you that. Even in simple cases, eventual consistency can be tricky and have some cost. So let's look at that operation split sequence again. And suppose that our operations are just arithmetic additions or maybe subtractions. So if you're version 0, the value is 100, you have all these things, +5, +7 in one split, +2, +9 in the other. If you were to achieve eventual consistency here, when they merge back together, you need the value 123 to show that all of those ops happened. But the key thing to note here is that version B and version Y, which are what you have at the end of each split, are by themselves not enough to generate the V4 value. You kind of have to know what the value was when these things split. And it gets more involved. You actually have to kind of know the version of the splits, because I drew you one simple split here, but you could have multiple splits. You could have lineages that start from scratch on a node that didn't have a copy of the replica. Your merge backs could be complicated. You may not be able to see all the things at once. You may be merging one lineage with another one that you didn't directly split from. And so it turns out you actually kind of have to be able to ID the record, you know, that goes with the value that you have at the split. So you need to know the versions and values at the splits. And you kind of either need to know when you're split or whole, when you're not split, to be able to clean up this history, or you're going to end up storing all the versions and values. And that is just, you know, now you're in a world where that's just a different kind of database if you have to keep track of all of this history for records when they're split and repair it when you think they're whole again. So in general, that was actually a pretty simple use case by most people's standards. It gets trickier. Operations might not be derivable from values, so you might have 4 going to 8, and if you know you're just doing arithmetic, cool, yeah, that was a +4, but if it could have been more operations, I don't know, other things can get you from 4 to 8 too. Similarly, previous values may not be derivable from operations. Obviously, something like a hash takes many different initial values to the same final value, but it's not just hashes. You can do things like an arithmetic mod, or you might have a list that you trim and select stuff out of, and you know, you can see what's left, but if I drop the bottom 10 things, I have no idea what the heck those were before this operation. And finally, operations may not necessarily commute, meaning they may not be order dependent. So if you're just doing arithmetic addition, yeah, +5, +3, same as +3, +5. But you can change some arithmetic here, and suddenly it doesn't work that way anymore. It matters what order you apply these operations in. And it's not just, you know, arithmetic operations. It's most things actually kind of seem to be this way, like string concatenation. You know, start with cat, append woman, then rules. That's very different to, you know, cat rules woman. So it's just a lot of things. It's just this is not an unusual thing. So the order matters. And so what that all means is you can't just store the version and value at split. You got to know all the operations and the times they happened since then, if you're going to try and cover every use case there is. And so now you're talking, you know, this is starting to get costly. It's like, you know, what are my records? Blockchains? You know, it's just, you're going to have to keep track of a lot of stuff, either forever or be fancy about knowing the state of your cluster and, you know, when your records split and become whole again to clean up history. So So yeah, I mean, it can get complicated, and certainly to do it generically is extremely complicated. Strong consistency systems, generally, you don't have to deal with this. You absolutely don't need any history at all. You can implement the system with the final version. You don't have to do this stuff. And so again, very different unicorns. So a lot of people might say, oh well, why can't I just use CRDTs? Well, CRDTs, all that is really a way of packaging everything I just said into the data type. And so the CRDT is also very, very use case dependent. If the CRDT is meant to handle a certain class of operations, it might be quite tractable. If it's a bigger class, it can get really hairy. A lot of effort goes into those things. But yeah, in general, they're incredibly use case dependent, and it's just really a neater way of packaging everything I just said. They're storing the history they need, and they're managing it in order to be able to recover the version, the final version of the record after the merge you want. I also get a lot of people that say, "Oh, just give me the two records, and I'll merge them," and that can be a heck of a thing in two ways. It often turns out that they end up saying, "Oh yeah, and we'll need the history too," But sometimes, even if they can somehow do an acceptable merge without much history, it's still just a sort of an application costly thing. You have to present these things through some notification scheme to the app. They have to deal with it. You have to write them back. So there are all sorts of costs there to that too. That's not generally as easy as people like to think. So yeah, in general, eventual consistency, very complex, and especially in use case dependent. So yeah, you just have to know that this is not just a stop along the road to strong consistency. It's something completely different. And again, reminding you that it is not, you are not in the C world of the CAP here. If you're doing eventual consistency, you are firmly in the A world. It's the high availability system. You're just trying to expend a lot of effort to minimize, or if you're lucky, eradicate the permanent data loss. But you're in an AP system when the splits are going on, and they can go on for a long time. Strong consistency is out the window. This is not strong consistency. Okay, so if you're going to choose a high availability system, maybe you have all these fancy CRDTs and so forth, and you can get your eventual consistency. But what it usually means is that people are choosing to lose writes. So again, back to our simple split scenario, or a simple split scenario, you generally end up with much simpler merge schemes when the cluster mends itself. For example, you can just pick the latest one. In this case, that means you lose two writes, Vx and Vy. Or maybe you have a policy where you pick the one with the most history, which in this case means you might lose the latest one. But either way, you're losing something there. Let me actually flip back to this guy where you pick the latest, just to hammer home the notion that eventual consistency is incredibly use case dependent. I can claim that this is eventual consistency if my usage model is such that these operations actually don't care about the previous value. Like maybe I'm just writing, my record is just the current position of something and I don't care where it was before. In this case, if I choose VA, well, that's what it would have been if I had a strong, consistent system. It would have, I would have ended up with VA anyway, because I'm just writing a brand new record, and that's what it would have been. So that's the ultimate demonstration of how use case dependent eventual consistency is. But yeah, generally what we're talking about is we're losing writes. So again, a quick summary. You're choosing A, you're going to allow these record progression splits, which, since you're allowing them and they're observable, by definition, you're out of the world of C in the Cap Theorem. And then your problem now goes down to conflict resolution of the split lineages. And that usually comes down to it being really complex and costly if you want to try to minimize loss or eradicate it if you're lucky. Or you choose something simpler and you're pretty much accepting that you're going to lose some rights in these scenarios. So that's just how it goes. If you're choosing strong consistency, what that generally means is that to do it, to actually make the guarantee, you have to disallow operations that would cause record version splits. So like in this split brain scenario here, I don't want to write to that guy out there on the right if that's all I can see, because that's just begging for a lineage split. So most systems will just say, yeah, you're not going to be able to write that. And so the record becomes unavailable, and that's your choice. But that's what you got to do usually to guarantee C. The other part of it is that you need to disallow observation of records that do actually get written in these cases where they shouldn't. And you might ask, well, why not just make it so that there are never any dirty records? I'd love to. We tried, but I kind of think now that it's hard to see how to do SC without having to deal with dirty records, because the bottom line is you can be in the middle of writing in a perfectly good cluster and it's just halfway through it made it to one node, and that's when the cluster partition happens and the other ones just don't get done, and so you're sort of stuck with this thing. And the job of strong consistency then is to make sure nobody sees that in an observed lineage from the outside, and then get rid of it as fast as you can. And that might mean that the right lineage version, when you do the merge back, just pretty much wins over that. And luckily, you don't need history and all of that to do that merge. It's just one record straight up winning over the other. Or it could even mean that when the cluster mends, you actually finish propagating that dirty record, and then if it gets to enough places, you define it as being clean, and you can go that way too, or both. Some systems maybe even do rollback if they know what the previous version is. I don't know. There are probably a lot of ways to do it, but I don't know of any way that I would be able to make a system like this that avoids the concept of a dirty record altogether. But yeah, generally what you're doing is disallowing stuff that in a AP system you would be allowing, and that means that by definition I'm not making maximum use of my availability. I'm disallowing transactions and telling you that records or partitions are unavailable, and that's the trade-off. So, different things for different use cases. Some things just have to have strong consistency. They just can't afford to see these weird intermediate records and missing rights and all of that. And other use cases, they don't mind some of that. They'd rather just keep rolling. And if it means some records end up being a little bit weird, or you lose some rights, maybe you can tolerate that. Okay, I said I'd come back and tell you about, within strong consistency, some choices of read-only behavior. So there's our single lineage, or single progression again, that's strongly consistent, but there are some nuances in read-only operations as to whether you can get away with some things. So I'm going to put down two different kinds of behavior that you can make your read-only operations follow. One, which I call session consistency. I don't know what the other names for this are, read what you wrote, so forth. I have a hard time with nomenclature in computer science. It sometimes seems like there isn't just one standard thing. But anyway, to me what that means is that a single client is never going to see a stale version. If you've seen v3, you're never going to see v2 again. You're only going forward from there. The other option I listed here is linearized, which means that even across different clients, you'll never see a stale version, meaning that client A can see, if client A has seen v3, then client B better not see v2. And just for the heck of it, I'll throw up a third option, the relax. We do have use cases where people don't want to lose the rights, which is the core definition of strong consistency, but they actually don't really care if they occasionally see a stale version, as long as it's not a dirty version. But usually the big question is, do I need my reads linearized or is session okay? That's the question I mostly get asked about read modes. And the reason people are asking is typically linearized is more costly, usually significantly more costly to deliver for a read, meaning it in transaction latency. My usual answer is to tell if you need linearized or not. Ask yourself whether, is there any way that you could verify that your system would know if linearization was violated? In other words, is there some external source of truth outside the database where if client A had seen v3, that you could tell that client B sees v2 after client A sees v3? And that could be two people sitting on their phone at the opposite sides of the city, asking them, "Did you see v3?" That counts if that's your external way of verification. But really, more often than not, it turns out that no, there isn't. And so, if there isn't a way that the different clients are going to be able to check whether they went backwards on what the other one saw, then you don't really need it. If all the client sees is all it sees, and it doesn't know or care what the other clients are seeing, then so it's a little behind. Maybe the other one saw v3 and I just picked up v2, but I'll eventually get there, and usually that's what people need. Anyway, so don't get these confused with the actual definition of strong consistency. They're their own thing. They may be important. You really may need linearized reads, but these are read modes or read-only modes or choices within strong consistency. You are in the world of strong consistency here. Okay, just quickly, I'm going to describe a traditional consensus system that guarantees strong consistency. Usually the way those work is that the replicas in the cluster are kind of in fixed places. They don't really move around. You do an operation that writes to all of them, and a successful operation is going to be defined as something that got written to a majority of them. So corollary of that is that you can get your 100% availability with n nodes missing as long as you have 2n+1 replicas, because you need a majority to have a successful write. Which then therefore means that just to do a rolling upgrade in this sort of system, you need at least 3 replicas. You need replication factor 3 to do this without losing any availability. One thing about these systems, they typically do preserve partial availability well by making use of all the connectivity. Any path you can take to get to write to the place you intend to write is taken, and they're actually pretty resilient to some pretty heavy P. But there are alternatives, and I said I wasn't going to talk about Aerospike strong consistency, so for the next slide or two, we'll call it Kevin's system. So in Kevin's system, I've drawn 2 replicas here. You'll see why in a minute. It's different to the traditional consensus system. Your operations are master-centric. They go through a master, and the master will replicate to the replicas. So it looks kind of like what just happened there in that graphic. In this world, successful operations are defined not as having written to a majority, but having written to your replication factor number of replicas. So in this case here, also 2 replicas. But interestingly, you can get 100% availability with n nodes missing with just n+1 replicas, which is a pretty neat trick. And that means that you just need 2 or more replicas to do a rolling upgrade with 100% availability. So this is a difference. We view it as a pro, Kevin and I. We think that's a good thing, because if you can run with 2 replicas instead of 3, that's, 3 is 50% more storage cost, and the transactions, it's 50% more network stuff just to write your records. So this is kind of cute. It helps cost and performance. On the other hand, our system is not as good as a traditional consensus system. It's pretty good in very simple P scenarios, but once the connections breaks start to get really prevalent, then we degenerate our partial availability pretty quickly. And you can concoct some schemes where a consensus system retains quite a lot, and we go all the way to 0 until the cluster gets mended. But, different things. So again, the pros for us are we just need fewer replicas to tolerate a given number of nodes down, or we can tolerate more nodes down for a given replication factor. And here you can also think the racks instead of nodes, if you have rack-aware, all these systems usually do. So it can mean lower costs and higher performance. And the traditional systems generally are much better at preserving higher partial availability in the severe P scenarios. So for example, if your cluster was all the nodes were a bunch of planes flying around, and you expect the connectivity to just be all over the map, then maybe you don't want to use Kevin's system. But maybe if it's a rack in a room that 99.99% of the time the connections are pretty good, then maybe the pros of Kevin's system start to look pretty appealing. Okay, so again, finally, this choice of C versus A is really all about which do you prefer on a very rainy day. Again, mostly light rain, like upgrades, that's not driving your choice. You get both for free in most system. C sacrifices A on very rainy days, other way around for A if you choose A. C can sometimes be more involved to deploy. It certainly is for Kevin's system, because the AP system is really nice in that you don't even have to tell the nodes in the cluster that what the cluster is supposed to be, but we actually have to do that for the CP system. So it can be a little more involved operationally. Sometimes strong consistency means it's less performance and high availability. In our case, that's not really true. And that was really the original motivation for trying this new way of doing it. That was our goal, and we succeeded. But yeah, in general, this is your trade-off. Am I done, or I'm done? Okay, so good. I don't have to talk about my optional slide. So thank you very much. So they're going to use the question session for the last slide. A lot of people have systems that they claim deliver strong consistency, and often they just don't. Maybe they don't know what it is, or maybe they just are disingenuous. But even if we're telling you that we deliver strong consistency, you shouldn't necessarily take our word for it. The Jetson tests are run by this guy, Kyle Kingsbury, who has sort of made a career out of this, of going around and being a third-party, one-man band verification method for strongly consistent systems. So he tests a lot of things. Like here, I just talked about a system with single record transactions. He does all sorts of other stuff. He'll do the multi-record transaction stuff, things like that. But we had him come to test our system. These days you pay him to come test your system, but he does not whitewash the results. It's not like you're paying him to do your PR. He will happily report any trouble that he finds at any stage of his investigation. So for us, he verified the strong consistency definition. He verified that we do indeed guarantee our single linear progression of record version. We do indeed never lose writes. He did measure our availability degradation, in extreme partition scenes, and he did verify our linearized read mode, which is the hardest one to deliver. So he put the system through the ringer. He was there for a couple of months, and he really digs in and tries to understand how it works so that he can try and break it. I mean, that it's not just that he's interested in it, but the better he understands it, the better chance he has of setting up his tests and customizing it to expose a flaw in your system. So he tried very, very hard for us for a couple of months, and then eventually resigned, conceded that he couldn't break strong consistency. Although it was, let me tell you, an interesting couple of months anyway. So yeah, if you're considering a system that claims to guarantee strong consistency and you think that's the thing that you need, or whatever whatever the system claims it's guaranteeing, you should go look at and see if he's tested this system and see what he has to say about it, because it's a pretty good outside look at, so you don't have to take the vendor's word for it. Obviously I'm telling the truth, right? When I say we deliver strong consistency, there's no question that that's what's happening. But actually it was nice too, because we tested the heck out of our stuff, but those are our tests. I was actually pretty interested to see, actually kind of scared. The 2 months, I felt like I was, it's a sword of Damocles above my head. Like every morning I wake up, oh no, we're going to go in, he's going to show that something's wrong and it's broken. And there are actually a couple false alarms in there that just, I nearly had a heart attack until we discovered they were false alarms. But yeah, he tried really hard, and so you can, if he's tested a system that you're interested in, you should definitely go read what he has to say. He's a little sensational in his reports. I mean, we passed, but it's it's still kind of you have to dig in there to see that. Okay, thanks. That was it.